Now we're going to talk about the fundamental theorem of calculus part 2. This one is the one you're probably going to see most often in terms of usage because it gives us an easy way of evaluating our definite integrals from section 5.2. If you recall that example that I did to evaluate the integral, I believe the example was the integral from 2 to 7 of 5x squared minus 4x dx. And what I did was I made rectangles. I plugged in the sample points not make rectangles. I found sample points, plugged them in. I got an equation for the sum, and I found a limit. That was a really long and tedious process to do. There is a much faster way of doing it. Now, there's a proof that we're going to go through to show you how the fundamental theorem of calculus came to be. We're going to use the idea of Riemann sums, and we're going to relate it to the antiderivative. Okay? So, the fundamental theorem of calculus part 2, here's what it says. If f is continuous on a to b, so all that means is if I have some function and it's continuous from a to b, then the integral from a to b of my function f of x and then dx is equal to big F of b minus big F of a, where big F of x is the antiderivative of any antiderivative of little f of x. This gives us a much faster way of finding the integral. What the fundamental theorem calculus part 2 is saying is that the integral is equal to the integral from a to b of some function is equal to its antiderivative evaluated at b minus the antiderivative evaluated at your lower bound, a. Okay, so what this is saying, if you remember what antiderivatives were, you undo a derivative, you go backwards, okay? So all you have to do is treat this as if it were the derivative, undo it to get your antiderivative, and then plug in these points, subtract them, and that is equal to your area. Alright, so we're going to go through the proof and see why this is, okay? How can we relate? Remember, this is a limit. This integral was defined as a limit of rectangles. How is the limit of rectangles, the areas of rectangles, related to the antiderivatives? Okay, how do I get this equality? How do I know that this is true? So in order to do this proof, we need to rely on the mean value theorem. So let's do a really quick review on what the mean value theorem says. And I'm going to put it in terms of our function and our derivatives, or our antiderivative and our function, okay? So here's what we know. Big F is an antiderivative of little f, okay? So if big F is an antiderivative of little f, that means big F prime of x is equal to little f of x, okay? We're going to need this fact later on, okay? Now, since big F is an antiderivative of little f, that implies that when we say antiderivative, we mean on the interval a to b, okay? On that interval a to b. So, if this is the antiderivative of this, this implies that big F is differentiable. So big F of x is differentiable on a to b. Take off the endpoints. Now, since it's differentiable on that interval, what we learned in chapter 2, differentiability implies continuity. If you know a function is differentiable on some interval, you know it is continuous on that interval. So f of x, big F of x, is continuous on a to b. So these were the two conditions of the mean value theorem. So then by mean value theorem, there is a C in this interval a to b such that mean value theorem. So remember this fact. We're going to come back to it. We're going to need it. Actually, we're going to need it in a second. Let me not write it or erase it. So such that, so I'm going to go up here now. Big F of B minus big F of A divided by B minus A is equal to big F prime of C. Big F prime of C. Okay? This is what the mean value theorem says. Okay? Go back, look at your notes, or look in the book. Look at the mean value theorem. It's exactly what it says. But now, we're going to use this fact right here in this instance right there. Big F prime of C, well, if F prime of X is equal to little f of X, then big F prime of C should be equal to little f of C. Alright, so I'm going to erase the conditions for the mean value theorem. I'm going to rewrite this, and we're going to do a little bit of algebra to just get it in a different form. Okay? So we got f of b minus f of a divided by b minus a is equal to little f of c. Big F prime of c is equal to little f of c, so all I did was substitute this piece in for right there. Okay? Now what I'm going to do is I'm going to multiply both sides by b minus a, and you get f of b minus f of a is equal to little f of c times b minus a. Okay, now, we know that our function is continuous on our interval a to b. We know it's differentiable on our interval a to b. So the mean value theorem holds. And from the fact that we know that big F is an antiderivative of little f, we can make this substitution just by this definition of antiderivative. With a little bit of algebra, we get this right here. Okay? That was just a recap of what we did. We're going to need this idea in the proof for the fundamental theorem of calculus part 2. Okay? So give me 1 second. Now, I'm going to erase this. We're going to come back to it. So, like, start it in your notes, okay? Make a note of it. We're going to come back to it. Okay, so let's look at the definition of an integral. An integral is from a to b of f of x dx is equal to the the limit as n goes to infinity of the sum of I is equal to 1 to n of x sub I star times delta x. Okay? That was just the definition that we gave the integral back in the last section, 5.2. Alright, so now delta x was equal to b minus a divided by n, and x sub I star is any, that's very key right here, is any sample point in the ith subinterval, xi to xi plus 1. Okay? So this xi star is any sample point in our interval. Okay? For this interval, this is our bottom of our rectangle. Okay? And we're just picking any point in that interval. When we actually did Riemann sums, we did left endpoint, so we picked this left endpoint of the rectangle, plugged it in. When we did right endpoints, we picked this one and plugged it in. When we did the midpoint, we found the midpoint of this interval and plugged that value in. Okay? So it doesn't matter what point we use on the interval, as long as it is on the interval, okay? Different points will get us better approximations. As we saw when we did the left and right approximation, the midpoint approximation was always better, okay? So again, this is very key here. These xi stars are any sample point inside the interval. Now, what we're going to do is we're going to rewrite this delta x right there. We're going to rewrite this delta x, okay? I need a little bit of room. Now recall what we started with when we did this definition. We said x0 was equal to a, xn was equal to b. Now, to get each xi, that was a plus I times delta x. Okay? Now, all we're going to do is redefine what delta x is. Remember, we split the interval up into equal-sized rectangles. Delta x is equal to b minus a divided by n. Okay, we don't want this definition of delta x. We want to change it. So let me look at xi plus 1 is equal to a plus, now, I plus 1, so this is going to be I plus 1, delta x. Now, really, I have these out of order. What I want to do is I want to subtract these two, okay? I want to subtract them, so I'm going to put this one on bottom. xi is equal to a plus I delta x. And if you were to subtract these two right here, so let's see, put a line there. You get xi plus 1 minus x sub I is equal to, subtract these, a minus a goes away. If I were to distribute this, I would get I delta x plus delta x. So I got I delta x minus I delta x. They go away, and I'm left with just delta x. See, all we did here was redefine what delta x was, okay? It's the distance between one endpoint of a rectangle and the other endpoint of a rectangle. Since we split the rectangles up into equal intervals, dividing it by n equals subintervals, this distance, it doesn't matter what subinterval you pick, the number will always be the same, okay? So, what we're going to do is we're going to take this piece, this delta x, and we're going to plug it in right there, Okay? So, this is equal to, the integral is equal to, we still have a limit as n goes to infinity of the sum of I is equal to 1n of x, of f of x star. Now instead of delta x, it's xi plus 1 minus x sub I. We used the definition that we got of delta x and put it there. Okay? Remember, these distances are always the same. We split the graph up into equal rectangles. Okay? Now, let's go ahead and examine that piece right there. Let's go ahead and see what that piece really is. Let me draw you a graph. Now, imagine we have a graph, just whatever it may be. Here's our A value, here's our B value. And what I'm going to do is I'm going to look at 3 specific points. Okay? I'm going to look at xi, xi plus 1, and xi plus 2. They're just some rectangles inside from A to B. Okay? I'm examining just one term of this sum. Okay? This is a sum of terms. I'm just looking at one term of it to see what it is. Now, we know that this is a continuous function, okay? F is a continuous function. It is also a differentiable function, okay? So when we're looking at it, it's nice, smooth, and curved, but for my illustration's sake, I'm going to draw it with straight lines, okay? So I'm going to look at kind of what this part is right here. I'm going to draw it like this. So the function looks something like this. You've got a point there, you've got a point there, and let's say it goes up a little bit and you got a point there. So it goes straight down, straight across. And let's make it go up a little bit more. So right here would be xi. Right here would be xi plus 1. Over here is xi plus 2. So we no longer need this. Now what we're going to do is we're going to apply the mean value theorem here. Okay? I know that looks like a sharp corner right there, but like I said, I just drew it for simplicity. Our function really is continuous. It is differentiable. There are no sharp corners. What we're going to do here is we're going to look at this subinterval right there, okay? Since we know that our integral is continuous and differentiable from A to B, then any subinterval from A to B must also be differentiable and continuous. Okay, if any subinterval is differentiable and continuous, we could apply the mean value theorem, okay? So on this subinterval, right there, by the mean value theorem, there's some f of x or I plus 1 minus f of xi divided by xi plus 1 minus xi is equal to, okay, oh, these should be big F's. Those should be big F's. So this is equal to, by applying the mean value theorem just on this interval, is equal to big prime of sum xi star, where xi star is somewhere on this interval. Okay, maybe it's right here, xi star. On this This value is the value that satisfies the mean value theorem. But if you recall the fact that we had previously, I'll show you. We don't need the picture. We did some algebra, and we found that f of b minus f of a is equal to little f of c times b minus a. Because we could apply the mean value theorem to any subinterval, we're just going to apply the same rule that we had for the entire interval. Just now we're going to apply for each subinterval. So this is f of x sub I plus 1 minus f of x sub I is equal to little f of xi star times xi plus 1 minus xi. Well, look at what we have right there. Look at what we have right there. So this piece right here is just a statement of the mean value theorem. This statement of the mean value theorem is equal to this. Okay, so let's go ahead and substitute it in. So I'm coming over here. Limit as n goes to infinity of the sum of I is equal to 1 to n of f of x sub I. Ooh, I was about to copy that. I'm replacing this for this. Big F of x sub I plus 1 minus f of x sub I. Brackets around those. And now let's go ahead and find the sum. Now, if you recall that the integral was related to a sum of areas, an infinite sum of areas, we manipulated this to just give it a form of the mean value theorem, and we picked this x sub I star so that it satisfies the mean value theorem. Because it satisfies the mean value theorem, we're able to make this substitution, which is a statement about the antiderivatives. So now you could see the connection between the integral and antiderivatives. Remember, the integral first was just defined as a sum of areas, an infinite sum of areas. But now we see that this infinite sum of areas can be changed into its antiderivatives. We could evaluate the antiderivatives to get the area for the integral. Now we're not done, okay? Now, in the mean value theorem here is really nice. I really like this proof. It's one of my favorite proofs. Here's where, I don't know, the magic unfolds right here. This sum right here. Let's see what happens when we plug in I. So, I equals 1. We get f of, if I plug in 1 here, 1 plus 1 is 2. F of x2 minus f of x1. Okay? So that was I equals 1. Now, there is still this limit as n goes to infinity, but it doesn't matter that this limit is here. Something else is going to happen. Plus, now let me go ahead and plug in 2. We already did I equals 1. Let me plug in 2. 2 plus 1 is 3, so this is big F of x3 minus big F of, if I plug in 2 into there, 2. Plus, let's do one more. If I plug in 3 now, you get big F of x4, because it's 3 plus 1 is 4, minus big F of x3. And then you continue on this sum. Remember, n goes to infinity. You continue on the sum until you get to the end. okay? Now, look what you notice, okay? Right here, f of x2, positive f of x2 minus f of 2. Oh, not f of 2. That should be f of x2. X sub 2. That goes away. At negative f of x1, there's no other x1s here. And then f of x3, positive f of x3, negative f of x3. This first term, f of x4, if you were to do the next one, there'd be a minus f of x4 over there. So if you see that every single term cancels, the only one that's left over is this one right here, which I think I realized I made a mistake at the beginning. I'll talk about that mistake, x1. Let's see, we could always rewrite this. So let me go up here with the sum. So if you were to keep going, plus, dot, 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 plus, you're going to get big F of x n minus 2. Oh, sorry, 1. Let's see, minus f of, no, I was right, 2, x minus 1. This was a bracket. Plus f of x n minus 1, n minus 1. I have these indices backwards. Give me a second. I have them written down. Let me see what paper it is. F of n minus 1, n minus 2. There we go. I had these switched. And then this one is an n, and this one is an f of x n minus 1. I'll rewrite that last part because I'm running into the edge of the board. F of x n minus f of x n minus 1. So that's if you were to continue the sum all the way to the very end. Now notice, positive xn minus 1, negative f of xn minus 1. They cancel. This term here would have canceled with a term over here. And then what you're left with is this very last piece right there. Okay? So, what we can conclude, I'm going to keep this piece and I'm going to keep this piece. We can conclude that this sum right here is equal to f of xn minus f of x1. What did we say xn was? Xn was b. So this is f of b minus f of, I believe I said x0 was a. This just comes into, I misindexed something along the way. It should have been x1 is equal to a. So that means this x1 is equal to a. Now we have shown that the integral from a to b of f of x dx, this is equal to the limit as n goes to infinity of the sum of these rectangles, xi star, xi plus 1 minus xi, which from here we applied the mean value theorem, which allowed us to get this summation, and then we went ahead and a lot of terms, every term cancels except for the endpoints. So we just proved the second fundamental theorem of calculus. Okay. Now there are other proofs to the fundamental theorem of calculus. You could prove the first part and use the first part to prove the second part. I like this way because it really relates it back to the Riemann sums and also the use of the mean value theorem. Okay. Now, the hard part is finding the antiderivatives. Okay. There are functions that don't have any antiderivatives. For instance, the integral of sine squared of x dx. I mean, you could stick on limits 0 to 1. That doesn't have a antiderivative, so we can't evaluate this integral. Okay, there are other methods on evaluating it, so don't think that just because it doesn't have an antiderivative, we can't figure out what this is. See, I'll give you another one that doesn't have an antiderivative. Integral of e to the x squared dx. That one doesn't have an antiderivative as well. See, there are a lot of functions that don't have antiderivatives, but a lot of functions do, okay? In this class, we've already learned how to undo the power rule, okay? In 5.5, we're going to learn how to undo the chain rule. And then if you take Calc 2, you'll learn how to undo products and quotient rules. But that's the goal here. Find the antiderivative, evaluate it at the endpoints. That is going to give you the area between of the curve between those two values. So let's look at our first example. Negative 1 to 1 of x to the 100 power dx. So what we need to do, here's our little f of x, is x to the 100. We need to find our big F of x such that f prime, big F prime of x is equal to little f of x. Okay? So we just undo the power rule. Big F of x is equal to, remember we go up one power and then divide by that number. So this is going to be x to the 101 divided by 101. So, how to evaluate this integral? Proper notation is like this. Is equal to, you're gonna write the antiderivative. We found the antiderivative. X to the 101 divided by 101. We're gonna put a line like that. Means evaluated from negative 1 to 1. So, all this is saying is find f of 1 minus f of negative 1. Plug in 1, plug in negative 1, and see what you get. Okay, so, see, 1 to the 101 power divided by 101. So that's this piece right here. Minus negative 1 to the 101 divided by 101. That's that piece right there. So all I did was find the antiderivative. I plug in the upper endpoint. I plug in the lower endpoint. Now I'm subtracting them. Well, this 1 to the 101 power is just 1, so I get 1 over 101. Negative 1 to the 101 power is negative 1. So I'm going to have a negative and a negative. It's a positive 1 over 101. So the answer here is 2 over 101. See, if I were to draw a graph of this, x to the 100th power looks something like a parabola. Now, this is not drawn to scale. If I were to draw like a normal 10 by 10, it's really, really narrow. So from negative 1 to 1, we just found that entire area underneath the curve and above the x-axis between -1 and 1. It's equal to 2 over 101. Okay? It's the exact area. And see how much faster that was instead of splitting it up into rectangles, plugging in values, and adding them all up and stuff like that. We just found the antiderivative, plugged in the endpoints, and did a subtraction, and there was our answer. Let's look at another example. The integral from 0 to 1 of 1 minus 8v cubed plus 16v to the 7th dv. So all we have to do is find the antiderivative, whatever that may be, plug in 1 minus plug in 0. So the antiderivative of 1. What would I have to take the derivative of just to give me 1? Remember, our variable here is v. Well, that's v. Okay? Minus, undo the power rule. Go up 1 power, v to the 4th. Now divide by this power. 8 divided by 4 is 2. Plus, go up 1 power, you get 8. So this is v to the 8th. And then take the coefficient, divide by the power right here. 16 divided by 8 is 2. So now I have the antiderivative. Now, if you remember back to when we talked about antiderivatives, anytime we found an antiderivative, we had a plus c right there. So where did it go? Okay, I didn't show you it on the last example because I forgot. Let's talk about it right now. We do have this plus c. So this is f of v. This is our antiderivative. So now to evaluate this integral, we need to find f of 1 minus f of 0. So plug in 1. 1 minus 2 times 1 to the 4th plus 2 times 1 to the 8th plus c. So I will highlight what I just did. I did this piece right there. I plugged in 1 into my antiderivative. So now here comes the minus. I'm going to plug 0 into my antiderivative. Well, that's 0 minus 2 times 0 to the 4th plus 2 times 0 to the 8th plus c. Well, this side is really easy. 0's gone, 0's gone, 0's gone. Oh, let me highlight what I did over here. So what I just did, I found big F is 0 right there. I plugged in 0 into my antiderivative. So the only thing that was left on this side was the c. But now let's look what happens to it. Plus c, distribute the minus over there, minus c. C minus c, these go away. So we don't have to worry about the c's, the arbitrary constants, when we do definite integrals, because they cancel, okay? So now we just got to figure out this part right here. 1 to the 4th, that's 1. 1 to the 8th, that's 1. So this becomes 1 minus 2 plus 2. Negative 2 plus 2 go away. This is equal to 1. So my final answer is equal to 1. So the area underneath this curve from 0 to 1 is equal to exactly 1. So you got another example. Let's see. It says the integral from 1 to 4 of u plus 2 and u minus 3 du. Now we have a product here. We can't integrate a product. We can, but that's a technique that you learn in Calc 2, integration by parts. what we're going to do here is the only tool we have is to antiderivative power rule. Okay, undo the power rule. If I were to multiply this out, you're going to get u squared minus u minus 6 du. Now all we have to do is find the antiderivative of this, and it's just undoing the power rule. So you get 1/3 u cubed, go up 1 power, then divide by the power, minus 1/2 u squared, go, this is a first power, go up 1 power, to a 2, divide by the number, and then this is just a 6, so it's going to get a u. You could think of this as u to the 0. If I go up 1 power, it's u to the first, divide by 1, you get that. We can leave off the plus c, evaluate it from 1 to 4. So all this is saying is take 4, plug it in, minus take 1, plug it in. So 1/3 times 4 cubed minus 1/2 times 4 squared minus 6 times 4. So that's just plugging 4 in. So this is f of 4 minus f of 1. Here's our f function, f of u. So here's this piece. This is 64 over 3. 16 divided by 2 is 8, minus 24. Let's see, 64 over 3 minus 8 minus 24. This gives you negative 32 over 3. Now if we find f of 1, and just plug 1 into here. Now plugging 1 in here is really easy. Cubing it, squaring it to the first power. So all that just boils down to 1/3, negative 1/2, negative 6. So 1/3, negative 1/2, minus 6. This right here is f of 1. So 1/3 minus 1/2 minus 6. This is equal to negative 37 over 6. So now we have both pieces. We have this piece. So f of 4 is negative 32 over 3 minus f of 1. F of 1 is over here. So negative 37 over 6. Now this is going to give us an answer. Let's see. Negative 32 divided by 3 minus a negative 37 divided by 6. Negative 9 over 2. Okay, so here is the area underneath the curve. Now if you notice, it's a negative area. If you recall, we are adding up positive and negative areas. Okay, so if you were to look at this graph, let's look at the graph of this thing. See, here are the zeros. So at negative 1, negative 2, 1, 2, 3, it looks something like this. The parabola. And we're going from 1 to 4. So here's 1, 3, here's 4. If you look, we've got so much area down there that's negative, and we only have a little bit of area that's positive. So the negative area plus positive area, there's more negative area, so that's why our final answer came out to be negative. Okay? Let me go ahead and do another example. See, it's a trig example. It says, what is the integral from 0 to 3 of sine of x minus e to the x dx? So all we have to do is find the antiderivative evaluated at 3 minus the antiderivative evaluated at 0. So let's find the antiderivative. F of x, big F of x. Well, what function do I need to take the derivative of so that when I take the derivative, I get sine of x? that's negative cosine of x, minus, what function do, if I take the derivative of it, I get e to the x. Well, going backwards, that's still e to the x. Here is my antiderivative. All I did was go backwards. If I take the derivative of this, I'm going to end up back here. That's one way you could check your work. So, this right here, going down over here, is equal to, okay, negative cosine of x minus e to the x, evaluated 0 to 3. So, plug in 3. Negative cosine of 3 minus e to the 3 minus, that's f, big F of 3, just plug in 3 everywhere. Negative cosine of 0 minus e to the 0. I just plugged in 0 into my antiderivative. Here you're going to need a calculator. Cosine of 3, irrational. E to the 3, irrational. Let's see, cosine of 0. Cosine of 0 is 1, but we got the negative in front, so that's negative 1. Minus, e to the 0 is 1. So this entire piece right here is negative 2. Negative, negative is a positive. So if you want the exact form of this answer, it's 2, I brought the positive 2 out front, minus e to the 3 minus cosine of 3, which you could plug into your calculator. I'll give you an approximate value. 2 minus e to the third minus cosine of 3. Make sure you're in radians. This is approximately negative 17.095. Alright, so there is 2 problems that I want you to go ahead and try. It's finding the definite integral, okay? So all you have to do is, exactly here, find the antiderivative of your function, evaluate it at your endpoints of your limits of integration, and subtract the values, okay? So pause the video, and then we're going to go through one more problem on finding the integral. Alright, so it says, sketch the region enclosed by the given curves and calculate its area. So this is going to be important when we get to chapter 6. We're going to have to be sketching the region enclosed by a given curve. So they give us the curve y is equal to square root of x, and they tell us y is equal to 0 and x is equal to 4. So let's go ahead and make this sketch. This is the square root function. So if y equals 0 is right down here, that's just the x-axis, so y is equal to 0. The square root function looks something like that, so here at 4, at x equals 4, right there, we're at 2. So this is the region enclosed. Okay? So what they're asking us to do, sketch the region enclosed and calculate its area. If we want to calculate the area, we just need to find the integral from 0 to 4 of square root of x dx. Well, this is a power rule. I'm going to rewrite it to the 1/2 power. If you undo the power rule here, you get 2/3 x to the 3/2. Evaluate it at 0 to 4. So, plugging in 4, you get 2/3 x, or not x, sorry, 4 to the 3/2 minus 2/3 0 to the 3/2. I plugged in the upper limit, 4, into the antiderivative. I plugged in the lower limit into the antiderivative. Well, this piece is 0, so it's gone. I just need to figure out that piece right there. So, the third 4 to the 3/2 power is 8. Okay? 8 times 2/3 is 16 over 3. So that's your answer right there, 16 over 3. The area enclosed by this curve, this line, and this line is 16 over 3. We used the integral to find that. I think I said I only had one more example. That's a lie. Now I have one more example. This is the last example. And it's by the given curves. Here's your curve. Sketch it. 2x minus x squared. And y is equal to 0. Let's go ahead and see what that looks like. So it's a downwards parabola because there's a minus sign right here, x squared. I could factor an x out. It has a 0 there, and there's 1, there's 2. Has a 0 there. It looks like that. It's not a half circle. This is a parabola. So don't think, you could think it's a radius of 1, calculate the area of a circle, cut it in 2. It's not what we're doing here. It's a parabola. So we're finding this area. So that just means take the integral from x equals 0, that's the start of the area, to x equals 2 of 2x minus x squared dx. Well, I just have to find the antiderivative. Antiderivative of 2x, x squared, minus the antiderivative of x squared. Go up 1 power, you can have x cubed. Divide by that power, you're going to have a 1/3 right there. So evaluate this at 2 and at 0. Well, if I plug in 2 squared minus 1/3 times 2 cubed. So that was the first piece, evaluating the upper limit, minus, I got to evaluate the lower limit. So I get 0 squared minus 1/3 times 0 cubed. This entire term is 0, okay? Sometimes it's really easy to plug in, especially if you have a polynomial, you integrate a polynomial, one of your limits of integration is 0. Really easy, it just goes away, you don't even have to evaluate it. So now we just got to figure out this. So this is 4 minus 8 over 3. 4 minus 8 over 3. See, this is 12 over 3. So we're going to get 4 over 3 as our final answer. So the area enclosed underneath this parabola and above y equals 0 is 4/3. Okay? So that's the end of section 5.4, or sorry, 5.3. Fundamental theorem of calculus is very, very useful for evaluating integrals. It cuts down the process of actually finding the areas of rectangles and doing a limit by associating the area with the antiderivatives. You find the antiderivatives, you evaluate it at the limits of integration, you subtract them, and there you go. There's your area.